Hello and welcome back. Today we're starting our series of tutorials on self-attention, and I've got a huge smile on my face because we've got some very exciting things coming up. All right, let's have a look at where we are so far. We've gotten up to so far. So we've talked about inputs and tokenization. We've talked about input embedding, positional encoding, and today we're starting on multi-head attention. Well, we're first going to talk about self-attention, and then we'll expand it to multi-head attention. And actually, to get us started, we're going to have a look at the research paper which we're dissecting. Attention is all you need. And so far, so this is the architecture, and so far we are here. We're at attention. And in this tutorial and the next one, we're going to be talking about this scale.product attention. And in fact, here's the paragraph. If you want to follow along, if you want to read this first, or afterwards, it'll all make sense once we've gone through this tutorial for these couple tutorials. All right, so let's get back into it. All right, so what have we got so far? Well, so far we've got these vectors which are have captured semantic meaning. So they, like fruit are fruits, snacks and treats are all similar. Then we've got adjectives, we've got nouns representing royalty, and so on, and a vector for every single word in the English language. So we've managed to create that, and they capture semantic meaning. Now we're going to take the next step, and we're going to upgrade the vectors to capture contextual meaning too. And this is the secret sauce of transformers. This is why they're so powerful, because they are able to capture the contextual meaning as well, and do so in an eloquent way. Let's talk a bit about what is this contextual meaning. Well, here's a sentence. The animal didn't cross the street because it was too tired. What do you think the word it refers to? Does it refer to animal or street? Well, for an English speaker, it's very easy to say right away that the word it refers to animal, of course. But if you think about it, how do we know that? Well, we know that because of this word at the end, tired. If we replace this word with a different word, wide, for example, the animal didn't cross the street because it was too wide, then right away things change. Now the word it refers to the word street because the street was wide. So as you can see, context is very important, and for us to be able to for a transformer to be able to understand the sentence and be able to work with it, it has to understand the context of each word and what the words represent. So the word it can represent either the street or the animal, and there can be many, many different examples of similar things. So how are we going to approach this? Well, we're going to take the vector for each word, as we've seen in the previous slide. We can code them into vectors, and then from each vector we will create three vectors: a query vector, a key vector, and a value vector. So there we go. From each single one of these vectors, we'll create three vectors. And in these tutorials, we'll find out how these three are created. In the next tutorial, we'll find out how they are used. All right, here we go. So there's vector x. They're going to be is going to undergo three linear transformations. So for each one, there will be a matrix that transforms this vector x into one of these vectors. And these three matrices are learned during training and are applied to any word x that gets to get its q, k, and v. So basically, we're going to our goal is to create a mechanism for the transformer to be able to create these three vectors. And how they're used, we'll find out in the next tutorial. But for now, we want to be able to allow the transformer to create these vectors and learn the way. So we're not going to tell it what to do. We're just creating an opportunity for it to create these vectors. So each of these three matrices has dimension of 512 by 512. So this is how it works. Here's our vector x. Here's the vector q that we want to output. Each one has 512 dimensions, and between them, it's a fully connected layer. So basically, again, in our neural network, basically it's a matrix of weights. Now, bear in mind that this is a linear transformation, so there is no activation function. Very important. It's not an activation function. We're not using the neural network here for the activation function. It's just to transform one vector into another. Then we've got this other matrix as well, similar thing, and this other matrix, a similar thing here. And note that these are all linear transformations, of course, no activation functions. And that's how we're going to get these vectors. Again, we don't have a designed objective of why we need these vectors or how they have to look, the transformer will decide that on its own during training, and how they're used we'll see in the next tutorial. And quickly, as a recap, in reality, these, of course, are all calculated in parallel. We've got our input nodes, and then right away, bam, we apply these three matrices, and these are calculated in parallel. That's how it looks. Hello and welcome back. Today, we're continuing with self-attention. All right, so previously we left off over here where every single word in our sentence has its own vector representation, and that's the blue vector. And then from that blue vector, we are allowing the transformer to create these three vectors using linear transformations. Now, at the start, these three vectors mean nothing because they're going to be created by linear transformations with random weights. So they're going to just random vectors. But over time, the transformer will learn to correctly utilize these vectors. We're just creating a mechanism for it to utilize them, and that's exactly what we're going to be talking about in this tutorial, the mechanism. So previously we learned how they're created, and today we're going to learn how they're going to be used. Okay, so in a quick high-level overview, what is going to happen is that the vector v is the most important one. Well, really, they're all actually important. All these three vectors are important, but vector v is where we want the transformer to store interesting information. So the word street has things that might be interesting to other words for context, to use in their context. The word cross, the word animal, the word because, they all might have something interesting, relevant to other words in the context, to use when context is created. So the vector v will be just coming from this vector, so it won't have any context in it, but it itself will be used when the context-aware vector will be created for each other word. And then the vectors q and k are just auxiliary vectors. They're vectors that will help us with indexing and deciding which vectors to use. So basically, in our situation, we're dealing with the word it. So we're going to take the word q. The procedure will be, we'll take the word q, the vector q, and we will combine it with each one of the vectors k for all other words, including for the vector k of the word it itself. So this vector k as well. So we'll combine q with each one of these one by one. Well, it's all going to happen in parallel, but these are going to be separate operations. So q will be combined with this k, and then with this k, and this k. And we will do a mathematical operation called dot product, which we'll discuss just now on the next slide. And then we will see which of these dot products are high and which are low. If a dot product is 0, then that means the associated vector v. So if this dot product is of q and this k is 0, as we'll see just now, then this vector v has no relevance to the context of the word it. If the dot product of q and this k is high, for example, it's close to 1, it can only, in the way we will set it up, it can only be between 0 and 1. If the dot product is high and is close to 1, then this vector is very relevant to the context of this word, and so on. So each one will be combined, and so q and k are just ways for the transformer to tell itself through training which words are important for context of other words, and v is actually the value that's going to be used for the context. So, and that's why they're called query, key, because that's kind of the indexing mechanism, and v for value. But that's a high level overview. Let's dive into the details and understand how this mechanism works. Okay, so here's the architecture of self-attention. Now, we're not going to talk about masking. There'll be a separate tutorial on that. It's not really important to us right now. And it's optional. It's only used in some situations. And this other thing, scaling, we won't focus on it because it's not a key component of this attention mechanism, but we'll mention a few words about it at the end of this tutorial. So the first part, this self-attention has two main parts. First part is how q and k are combined to get a indexing value. And then 2 is how this indexing value is combined with vector v to get the value, to get the context-aware vector in the end. So let's see how this works. So this query key indexing, by the way, this is just it's not a technical term, it's just something that I use for this tutorial because it's kind of makes sense of how this thing works. So here's our vector space. Don't forget it's a 512 dimensional vector space. We're only showing 3 here. And then we've got these k vectors for the words. Again, at the start they're random, but it's up to the transformer to do those matrix operations, those linear transformation we discussed in the previous tutorial, in such a way that this would all be useful to it. And so here are the k vectors, the key vectors, and then we have a query vector. And in this case, we have it for the word it, which is of interest to us right now. We're creating context for this word. So that's why we have the q vector for this word. Now, we're going to apply dot product operation to this vector in combination with each one of them in one by one. So a dot product between these two, a dot product between this one and this one, this one and this one, so on. So what is a dot product? Dot product operation is for two vectors. It's equal to their lengths multiplied by each other, multiplied by the cosine of the angle between the two vectors. So if two vectors are pointing in similar direction, like almost in the same direction, then their dot product will be high. If two vectors are perpendicular to each other, then the cosine is going to be 0, and therefore their dot product is going to be 0. And what we have is a multidimensional space with 512 dimensions, and it's very likely in that in a multidimensional space that two given vectors are going to be perpendicular to each other. There's just so many dimensions that the chances of them pointing in almost into similar directions is very, very low. And so the resulting dot products are all going to be very low, very small, almost near 0. And it's up to the transformer. This is its job during training, to understand how to set up those matrices, to learn the matrices, the weights in the matrices in the linear transformations we saw in the previous tutorial. It's up to the transformer to set up the weights in such a way that the relevant word's k vector will have a non-zero dot product with the word that we are interested in. So it's not our job, we're just creating a mechanism for the transformer to do what it needs to do. It's the transformer's job during training to use that mechanism correctly, to learn how to use it correctly, and set up the weights in the matrices. That's part of the learn process, so that this will be non-zero because it's relevant, and the ones that are irrelevant will be 0. And then on top of the dot product, we're going to apply over here, we can see the softmax operation or function. And basically we take all of those values, zi, in our case will be the dot product. So we take the value what we get, and we take an exponent of that value. So big values are going to become even bigger, small values are going to become even smaller, and then we divide by the sum of those exponents. So we normalize so that it's all, so the result is between 0 and 1. And what this does is it exaggerates the variation in dot product. So large dot products become huge, small dot products become tiny, and then it's all normalized from 0 to 1. And as a result, we'll get these kind of values where the vectors that are irrelevant, that are not pointing anywhere near in the same direction, will have 0 or almost zero results over here after the softmax. But the vectors that are relevant, for example, animal, might have a value after the dot product and after the softmax of 0.7. Another word might have 0.05, another word might have 0.2. So the relevant words will have non-zero values. And then from here, that's where we get up to here, right? So we get these indexing values, and then from here we're going to apply this. So that was the first. The dot product is this first matrix multiplication. The second matrix multiplication is when we take this result and multiply it by the vector v's. So here we have each vector v for each word. So animal, didn't cross, and so on. So for example, in this case, what we have is that the word cross or didn't are irrelevant to the context of the word it. So they get zeros. So as a result, they're not going to be included in the context. Whereas the word animal, as a result of all of this, has a 0.7 coefficient, and it's going to be relevant to the context of the word it. So is street, so is it, but with smaller coefficients, less relevant. And tired is going to have a high coefficient, it's a high-ish, semi-high coefficient because it's relevant to the context of the word it. And so from here, we're going to take a weighted sum of all of these values, and that is where what we'll get on the output over here. So here are those vectors, right? So by the way, these are not just values, these are vectors. So each one of these vectors has 512 dimensions. And so we can plot these vectors here, and the resulting vector will have a lot of the word animal, so 0.7 of each of the 512 dimensions of the word animal, about 0.2 of the word tired, of each of the dimensions of the word tired, then it 0.05 and street 0.05. And that's our resulting vector A. And that's how all of this works. And as a result, what we get is this vector A is a context-aware vector representation, or context-aware vector representation of the word it in our sentence. So that is not just what we had at the start with those blue vectors, but it's actually a context-aware representation. And by the way, we're going to do this for each word. So we did it for the word it because it's important. That's the word we were looking at, but this would happen for each one of the words. We would get a resulting context-aware vector. And before we wrap all of this up and summarize it, I just wanted to say a quick note about the scaling. The scaling is necessary in order to make this Softmax stable and so that the whole training works. They just found this, that it helps with the training and helps with everything working out very well. It doesn't have a specific, it just basically scales the dot product values. It doesn't have a specific, very important role in this whole mechanism. And now summing everything up. So we've got this context-aware vector. Here's where we started. We had vectors for each word. These vectors are, they have meaning, they have semantic meaning of each word, but that's the dictionary meaning of each word. But they don't have any knowledge about how the words are used in the context in the sentence. So then we created these context-aware vectors using, not context, so then we created these auxiliary vectors using linear operations, as we discussed in the previous tutorial. From them, using them, we did the scale.product attention. And from the scale.product attention, we got basically, here's our sentence again, just copy paste it. But here now, this word it has a new vector, a context-aware vector. So this vector has knowledge about of course, the dictionary meaning of what the word it's representing, but also how it's being used in the sentence. So it's got a bit of tired in it, it's got a bit of animal in it, it's got a bit of street and other things in it that are important to the context of how this word is being used. And moreover, we're not going to do it just for one word, we're going to do this for every single word in this sentence. And as a result, each one of them will get its own context-aware vector representation that takes into account how that word, that specific word, this word or that word, is being used in the sentence as a whole. Whew, there we go. That was the overview of how this scale.product attention works. And I hope it all adds up now. It all makes sense. Very powerful mechanism, and that's what makes transformers super, super powerful. They don't just know what the word means dictionary-wise, they also know how it's being used. And again, we just created this mechanism for the transformer. We gave it the opportunity to use the weights and learn all these vectors in the right way, and that's exactly what it needs to do through training. And thankfully, we have so much training data in the world, whole internet of text, and we'll talk more about training in a separate tutorial. Hello and welcome back. Today we are finally tackling multi-head self-attention. All right, so far we've talked about scaled.product attention, and that took quite a few tutorials because that's the heart of the transformer. That's one of the most important parts of why the transformer is so successful. And today we're going to take it to the next level, and we're going to talk about multi-head attention. And good news is that because we've covered these tutorials, this is going to be quite easy because multi-head attention is basically relies on scale.product attention. All right, let's quickly recap of what we discussed previously. So previously we talked about that attention, or single head attention, requires the word vector to be split, or not split, but 3 new vectors to be created with matrix operations or linear transformations from the word vector. We talked about how that's done. The Q, K, and V vectors, a query, key, and value vectors are created for every word. Then we talked about how they actually work and how from these 3 vectors we create a context-aware vector representation for every single word. And so what we end up with is a context-aware vector representation for each single word. Okay, so that was simple attention. Now, multi-head attention. It's very similar, but instead of creating 3 vectors for every word, we're going to create 8 sets of 3, right? So there's 2 sets, etc., 3 8 sets of 3 vectors for every word. So that means 8 attention heads in total. Each attention head, it has its own Q, K, and V vectors. This is for every single word. The important note here is that each attention head has its own independent 3-weight matrices. So there used to be 3 of them for every single word. Now there's going to be 24 of them because there's 8 attention heads times 3 matrices. And by the way, the number of attention heads is something you can tweak in the transformer. You can have more attention heads, less attention heads, is up to you. But in the standard paper, the way it was written, there's 8 attention heads, and that's what we're going to go with. So there's total 24 matrices, and they are completely independent. So they're trained independently, and that is important because it facilitates different kinds of attention happening in parallel, and we'll actually see that in action in an upcoming tutorial as well. But just for now, keep in mind that it's not the same matrix all along. It's every single time, and every attention head has its own 3 independent matrices. Now, and how does this work? Well, in the vector the vector x gets transformed into vectors q1, k1, and v1, for example, in the first attention head, using a linear transformation or matrix. And this is very important. You'll see tutorials out there where they say that this vector is taken and cut up into 8 pieces, and then they are sent their separate ways. That is incorrect. The way it works is this vector with 512 elements or features to it, it actually goes through a linear transformation where the matrix has a dimension of 512 by 64, and the output vector is therefore 64 in height, or 64 has 64 features. It's very different to just cutting up the vector x into 64 parts and then sending it through the different elements, because that way the different attention heads only get 64 features each, only get information about 64 features. Whereas here in this approach, where you're using a 512 by 64 matrix and you're using all of the 512 features, well, exactly that. Vector q1 has access to all 512 features through this linear transformation. They can all be combined to create q1, and same thing for k1 and same thing for v1. And then for q2, again, q2, when it's being created, it will have access to all 512 features. It's a very important distinction, and yeah, this is the correct way that it's done. All right, and then from there, all of these are taken. Let's just look at one attention head on its own. The Q1, K1, V1 attention head. All of these are taken. They're put through what we already know, the dot product, the scale dot product self-attention, which we discussed in the previous tutorials. And as a result, in the output, we get this attention vector or context-aware vector representation of word X, which is a 64-dimensional representation. And yeah, and that's basically, it's context aware already. But the thing is, it's only 64 dimensions. So what we're going to do, each one of these attention heads will get, each word gets 8 attention vectors. So this is the first one from the first attention head, from this one. Then from the second one, we'll get A2, and so on. And then from the 8th one, we'll get A8. And these 8 vectors are then concatenated into one vector with 512 dimensions. So we take A1 over here, A2 over here, etc., A8. And then we put them all together, we concatenate them, we stack them on top of each other, and that's where we get this 512 dimension vector. And that's kind of where the confusion comes from, because you add them up here, it feels like you would cut this vector up at the start. Remember what we were talking about, but that's not the case. Here, you use the matrix operations to go from 512 to 64 vectors in each attention head, whereas when you stack them, when you want to go back to 512, then you do stack them back up together. But that's not all, because here they just stacked up on top of each other. Now we want to mix it all up, or combine all of the things that attention 1 learned, attention 2, attention 8. It would be very arbitrary to just leave them like that, so that they're separate. What if the transformer needs an opportunity to combine the attention knowledge that it has developed? And so we're going to pass the resulting vector is going to pass through a final linear transformation to combine everything. That's where a vector A with 512 nodes, that's the vector, goes through a 5 by 12 by 5 by 12 linear transformation matrix. Again, don't remember that there are no what are they called? Activation functions in any of these linear transformations, just basic, simple linear transformations, basically fully connected layers. And then the vector A goes through this matrix, and on the output, now everything is intercombined. So whatever A1 learned, A2, A8 learned, the transformer has an opportunity using this matrix to combine all of this and get this output vector O. O stands for output, A stands for attention, and basically in the end we get same thing as we got with simple scale dot product attention, but this time it's combined through multiple heads. But again, it's a context aware vector representation of the word it in our sentence. In this case, well, it, or whatever word we're looking for. We were looking at the word it in this particular example, but it could be any word. And each word, just keep in mind that each word will have this output created for it. It will have its own context-aware representation. So there we go. In a nutshell, what we discussed about scale.product attention was a stepping stone. It is important, but the transformer architecture actually uses multi-head self-attention. So it uses multiple of those scale.product attention, and this is how it works. Hello and welcome back. In the previous tutorials, we discussed how scale.product attention works in the transformer architecture, and also how multi-head attention works in the transformer architecture. And today we're going to look at an illustration or visualization of how it works. So if you search on Google tensor to tensor collab, just search for this, you will be able to find this link on Google Colab, which is maintained by Google as well. And if you scroll down, further down, here, you'll find the visualization of attention. And by the way, when you first come across it, it will have 0 here, and it will have all of these switched on. Yep. So, and it'll have all. So basically, they're taking that sentence, the animal didn't cross the street because it was too tired, and they're translating it into German over here, and using transformer architecture. And this visualization shows us how attention works. So we're going to play around with it. So we're going to we're not going to talk a lot about layers at this stage, but let's just we'll cover layers in a separate tutorial. We haven't talked about them yet, so just put it on layer 5 for now, and then attention, instead of all, let's just put input on input. And then to make things simpler, let's just keep one of them. Let's keep the red one, for example. So if you go through these output words, you will see how they're attending. And we were interested in this word it, right? Like, is it the animal? Is it the street? Which one is it? And here you'll see that, so when you keep if you keep your mouse here, you'll see that its attention is paying attention to the word animal and to the word street, right? But to the word animal a bit more. And this, by the way, there's 8 of these colors here, and they represent the different attention heads. So in this attention head, it's taking into account a lot of the word animal, a bit of the word street, and some other words. And you can play around with this, and you'll remember that for us, it was very important what the word on the end was. Like, it was too tired, right? So if the word on the end was, for example, it was too wide, then it means the animal didn't cross the street because it was too wide, meaning the word it would refer to street, because the street was too wide. But if it's tired, like is in this case, the animal didn't cross the street because it was too tired. Clearly, it wasn't the street that was too tired, it was the animal, right? So then in that case, it refers to animal. So here you'll see that it's not paying too much attention to tired, but that's totally fine, because if you switch over to a different layer, so let's say we switch over to, not layer, so if you switch over to a different attention head, in the green one, you can see that it is very carefully paying attention to the word tired, to the word was, which could also apply to street, but also very keen attention to the word tired. And so that's how it knows that the word it probably refers to the word animal, to the word animal. So you can keep playing around and see what other sorts of attention is being taken note of in this architecture. Now make sure to check out these videos on the right or the full course in the description to continue your learning, and I look forward to seeing you there.